Hi guys, welcome back to UGC lecture series on lasers and their applications and the Swayam portal. The last few lectures I had given you what are the properties of lasers and what are so special about lasers, how did they acquire such a special properties, all those things were given. Also, I had given some typical examples of few types of lasers, some gas lasers, some liquid lasers, some solid state lasers. Now, we will go into the application aspects of lasers. This is something something totally unexpected for even for laser physics for us. We never expected laser will have such a wide range of applications. Perhaps I give an example of scissor. You know scissor and the screwdriver, all these things are very common tools. Scissor, you can say it was first used to cut paper, let us say. Now you have a very big scissors and very small scissors. You have hundreds of applications of scissors and screwdrivers. In a similar fashion, lasers have enormous applications from mechanical engineering, electrical engineering, electronic engineering, medical field, industries, cinema. All these things have enormously benefited by variety of applications of laser. What is funny point is, it is just a tool. Already you have a screwdriver, you have pincers, you have a scissor, all those things are there in the box of a toolbox of an engineer. He will take a tool and use it the way he wants it. This is the situation has come to lasers. There are so many varieties of lasers. Choose what you want and apply where you need it. That's all. Now, all these put together has made laser is an essential, unavoidable tool of modern technology. All this because of one single property. It is a source of coherent light. We have already mentioned coherence means temporal coherence and spatial coherence, or for all our public applications now we will say this is a source of light where you can get enormous number of photons of a single wavelength. That is all. If I put a lens before a laser and focus it on the focal point, the brightness is very high. Brightness is a technical term which means plenty of photon, which is a measure of photons available over a small area per unit area, photons of same frequency, that is what is the same quality available on a very small point. That is the meaning of this one. This property is the one which is made it as a unique tool. For our purpose, we will divide laser application into two broad categories. In one, laser acts as a passive tool. In another, laser acts as an active tool. What does it mean? Let us take an example. You ask somebody to come to your home. Imagine that person is just a postman or a courier. What he will do? He will just bring the packet or the letter, hand it over to you and go away. That is all. He will not do any other changes on the packet that has been sent by your father or mother or your friend, whatever it is. He is not supposed to do anything on it. He is supposed to deliver at the doorstep. On the other hand, if you bring somebody, a mechanic, to change a small part of the house, he will come with many number of tools, and after working in your part of your house, the house will be totally different because he will be doing some active active role in your house. The first one, he is doing a very passive role. In a similar fashion, in the low power laser applications, the object does something on the property of laser. In active application, the properties of laser does something on the object. Let me repeat. In the passive applications, object does something on the properties of laser beam. In the active applications, the laser is doing something on the properties on the target material. Now, first let us take the passive application, for which you need a laser, low power laser is okay, but it should be a pure good quality laser. Go back to the same application. A courier, a postman is supposed to bring and leave it to you. He is not permitted to touch or find what is there inside. He will honestly hand over, deliver it without doing anything on the post that you have sent it. That's a property of the courier. In a similar fashion, in a passive application, laser will bring the message and deliver the message to you. One such application is laser communication. In laser communication, you send a music, you send a video file, and laser is a courier. It comes from somewhere and comes to your house, hands over everything to you, and it just goes away. That's all. And it should be faithful reproduction of the sound or a video message you transmitted from somewhere. That means the laser should be very pure in quality and capable of delivering it without getting itself damaged or transformed. So, first let us take the passive example. I will show you some of all these things are already I have mentioned, but to bring back to your memory, the common at the present day situation is the spatial coherence would be around few millimeter, say 5 or 6 millimeter. The temporal coherence means the spectral width of the laser can be of the order of few thousand megahertz, or be measured in terms of temporal coherence length, about which I already have mentioned. A coherence length means that spectral width multiplied by the time will give you the coherence length. This will give you a measure of temporal coherence of the laser. Spatial coherence will be usually around 3 or 4 millimeter. Now, for a good quality laser easily available with a helium neon laser, it can be about 2.5 centimeter or even 25 centimeter. You might wonder, what is this 2.5 centimeter or 25 centimeter? Go back to what I have given about march past of the soldiers in a Republic Day parade. A laser, for example, a helium neon laser, let us take for simplicity, it has a frequency of, let us say, 10 power 15 hertz. That means in 1 second the wave will go 10 power 15 times. That is the meaning of this one. That is a frequency. Then the light will travel in 1 second 3 into 10 power 8 meter. Now multiply these two, that means in 1 second the light will travel so much distance with so many frequencies. You understand? You must remember 3 into 10 power 8 meter distance will be done by the soldiers with 10 power 15 steps up and down with a very orderly fashion. That's enormous number of movements, very big number of movements. This is all happen in about 1 second, and the distance covered will be so high. Now, in a similar fashion, calculate in 25 centimeter how many steps the wave will make. In all those steps, it will be very orderly. It's a stupendous number of steps. That's what it means. That means laser remains in proper steps for such a long time, long duration, long distance also. Now, next important point is the divergence. The divergence, we know ordinary light has a divergence of about 2 pi radian, which is about 4 radian. Laser will have a divergence of about only 2 milliradian, many thousand times small. These are the properties that we are going to make use of it. A diode laser, with which you are all familiar, I have shown you at the beginning, will have a divergence of about 2 to 3 milliradian. A specialized laser can have a divergence of even less, 0.5 milliradian. An N2 laser will have a divergence of typically 10 milliradian. What is important is all these are in the range of few milliradian, whereas ordinary light will have a divergence of 4 pi radian. Okay. Now, with this, one idea has been brought to the focus. Again, we can classify laser into another broad fashion. One is CW laser, pulse laser. CW laser means continuous wave laser. You have seen a diode laser or a helium laser, some of you could have seen. When you just switch on, the light will keep on coming out as a red nylon wire or a green nylon wire. On the other hand, there are certain types of laser like a ruby laser or a neodymium laser, where the laser will come as a bullet, like a raindrop. They will come one shot, another shot, and like that they will come. These are called pulse laser. The pulse duration can be of the order of millisecond, microsecond, or nanosecond, picosecond, or a femtosecond. Femtosecond means, you know, the time duration is 10 power minus 15 second. Is extremely small even. Such a laser has been produced in recent time. Even they have gone up to attosecond laser. I think 2023 or 24, I think 23, Nobel Prize was given for invention of a new types of laser which produce attosecond pulse, 10 power minus 18 second pulse. That is perhaps the smallest event that has ever taken place in the whole universe. What I am saying is, in the whole universe there are many big things. Such short events are not available in nature. 10 power minus 18 second is not to be found anywhere in the nature, but it has been produced artificially by human efforts. That is a few attosecond lasers that won Nobel Prize last year. I have given all this point. Now, let us see another important one. Power also is something interesting. You can have a low power laser. A diode laser will have 1 milliwatt, 2 milliwatt. Carbon dioxide lasers, which are commonly available in medical field, in dermatology, people use CO2 lasers so commonly. That will have a power of about 1 watt CW. But you can have pulsed CO2 laser of 10 power 15 watt, that is a very big laser. Not only that, only in CO2 laser you can have 10 kilowatt continuous wave laser also. Such a laser will be it will be like a big drum. You can just walk into the laser. Not when it is working. When you want to repair it, it will be the size will be very big. Such a lasers are available. And not only gas type, gas dynamic lasers, there are so many types of lasers which I have not described. Such big lasers are capable of producing enormous amount of continuous wave. On the other hand, in the pulse laser, perhaps I would say neodymium glass lasers, they have given the highest power of about 10 power 15 watt, but it is a very short duration of the order of few picosecond or a nanosecond. They are useful for thermonuclear fusion process. I have just classified all of them. Now, we will go into the detail. I should just add a few remarks. You have laser almost in all wavelength. That is the funniest point. You can get a continuous wave laser, I mean wavelength ranging from 300 nanometer up to 800 nanometer or even 900 nanometer. Let us say 300 nanometer is one side. This is the ultraviolet A or B, that is one side, goes all through the visible spectrum, then it will end up in the infrared. Now, leave alone ultraviolet and infrared, our visible range is very simple, easy to remember, is 400 nanometer to 800 nanometer. Below 400 nanometer you say ultraviolet. Just above red we say infrared. Now, tunable lasers are available particularly in semiconductors easily from 300 nanometer to 900 nanometer, such a wide range. Now, why you have such a wide range? Each application may demand certain particular wavelength only. I cannot use any laser for any kind of application. For example, for ophthalmology, optical photorefractive keratomy or retinal welding, retinal coagulation, the best laser is a green laser. Such a laser is available most efficiently from argon laser. Other wavelength lasers are not suitable for this one. Similarly, for photorefractive keratomy, that is correcting the eye, the curvature, cornea of the eye, the best laser is a nanosecond or a picosecond laser at 195 nanometer or so. A typical eczema laser is the most used. So, depending upon the requirement, we have the facility, we have the opportunity to choose the laser. That is why we say it is a very versatile laser. Next one, we shall see when we say, another way of looking at this one is, a certain set of lasers are used for diagnostics. Diagnostics means the laser light will fall on something, get the information from that. From the information, you will come to know what is the property of the sample. One such example, maybe you must have heard about it, we can shine a laser on a tissue, whatever comes out as a reflection or as a Raman shifted signal can be captured by a CCD camera, analyze, and then it is possible in principle to tell the patient that what you have is a tumor which is a benign tumor, or the doctors would say you have a tumor which is in the initial stages of cancer. One such thing is leukoplakia. Oral cancer can be easily detected, or the doctors can say you have already a second grade laser, third grade laser. All these things could be analyzed using the reflection and scattering from a suitable laser. This is what we mean by diagnostics. Okay, we shall go into the variety of applications. First, I will take diagnostic applications, where laser will carry the message or information from the object. That is all it means it. So, the easiest one is metrological applications. This metrological applications, which metrological means measurement of something. You want to measure the size or the distance or the shape or whatever it is. That is called the metrological application. For such a laser, the easiest and the most commonly used one is helium-ion laser of 2 milliwatt. For example, the wavelength is given. This is 633 nanometer. The divergence usually about 1 milliradian. And then if we have seen the first few lectures, I had shown you that when the laser beam falls, laser beam travels in a smoky room, you will have something like a scintillating, beautiful brightness, which is something you must see to believe the special property that is called a speckle. That particular speckle property itself, I mean, if you allow the light, laser light to fall on rough surface, from the ups and downs, the hills and valleys of the rough surface, light gets reflected, and light, the eye is a lens, it will focus on your retina. When it focuses on your retina, the eye is capable of discriminating the dark and the bright spot. When it sees the dark and bright spot which are random, that is called the speckle. What is important application of point of view is, if the surface is rough, speckle is different, it will be bigger. If the surface is very small, the speckle will be so smooth that you will not be able to discriminate. That means this particular application can be used to find out the surface roughness of any finished product. As simple as that when I said it, but doing this experiment, calculating and calibrating all this is a big process that is called metrology, laser spectral speckle metrology. That is a domain by itself. Whatever I have said is an extremely small example of how laser speckle by itself can be used in a tough mechanical engineering application. Next one will be alignment. Yeah, alignment is a major application in the civil engineering. People will be using, even now people are using ordinary light, but in some precise alignment, a long tunnel, ordinary light will not be of any help. In those points, people have started using the same helium-ion laser. If you look at the picture, you can easily follow it up. You see, when the laser beam comes out, as shown in the beam, shown in the figure, it will come out a simple a circular beam of 3 millimeter or 4 millimeter diameter when it comes out. But as it travels, 3 millimeter will become 4 millimeter, 5 millimeter, 6 millimeter, like that one. It narrowly just, it will become a cone of light with very narrow divergence as shown here. Then all that you have to do is put an object one after another, just if you can put an object which is blocking the first ring, then you can put another one which is aligned with, I mean, just imagine you have a long tube in a corridor or something. You put one hollow tube where it just allows only the first ring, then the laser has come out. But by the time it has come out, it has expanded. You must remember, it has expanded little. So, in a tube of 5 meter length, you are going to put 5 meter length one after another, all in a straight line. All that you have to do is put one tube here, so that one ring, the first ring just comes out, and it comes out, here comes. You put another tube, that tube will just cover the second ring, because it has expanded. Like that you can keep on putting one after another. Eventually you can have a tunnel of 1 or 2 mile length using this kind of alignment, as I shown. Another possibility is, this is called a 4-quadrant technique. What we mean by 4-quadrant technique is, you have 4 detector, optical, optoelectronic detector. You see the 4 rings are there. 4 rings are 4 detectors which will, let us say optical diode for example. When light falls on left side corner, left corner, it will respond, show some current. Now, what all I have to do is, I put my tube with this 4-quadrant detector on the 4 equal sides. Then if the light is falling this side more, it will show more current, this side less. In that, if my tube is more, it's not blocking properly, it's not properly cutting the light. This light, the light from this particular photodiode will be more, this will be less. So, all that I have to adjust is, keep on adjusting the long tube such that all the 4 photodiodes, photodetectors just show equal intensity. When they show equal intensity, it means they all cutting the ring, the tube ring is cutting all the 4-quadrant photosensitive detector equally well. If it is equal, that means it has centered, it has been properly aligned. That is the meaning of this one. This is something which has been very useful in laying the long tunnel in the coal or any other mines. There is another important application which is called Michelson interferometer, to measure extremely small change in the length. This is something fantastic, which we will take it up in the next lecture. Thank you very much.